Welcome to the second outcome, all about spotting and measuring straight line relationships between two quantities. We'll plot scatter graphs, fit the least squares line, y equals a plus bx, and then use it to make predictions. Here's the plan for this outcome. We'll plot a scatter graph from paired data, get to grips with the idea of a line of best fit, and then calculate the regression line, y equals a plus bx. After that, we'll interpret what the gradient b and the intercept a actually mean, plot the line, and use it to predict, all while keeping a careful eye on the difference between interpolation and extrapolation. A few terms to set up first. Bivariate data just means paired data, two quantities recorded for each item, written as an x and y pair. A scatter diagram plots each of those pairs as a single point. Correlation describes how closely the two variables move together in a straight line. The line of best fit is a straight line drawn as near as possible to all the points. And when we calculate that line properly, we call it the regression line, I equals a plus bx. Let's think about where this data comes from. Every item gives you two measurements, say a person's height and their mass. We call one of them the explanatory variable, x, and the other the response variable. I plot each pair as a single point, and the pattern those points make reveals any relationship between the two. That picture is what guides all the calculations that follow. Plotting a scatter graph carefully matters. Draw your axes with x across the page and y up it, and choose scales that fit the full range of the data. Label each axis with its quantity and units, then mark every pair with a small cross. Crucially, don't join the points up with a line and give the graph a clear title. Let's plot 1. 5 students recorded their hours revised x against their test mark y 1 and 2, 2 and 3, 3 and 5, 4 and 4, and 5 and 6. The x values run from 1 to 5, so we'd scale the x-axis from 0 to 6, and y runs from 2 to 6, so scale that from 0 to 8. Mark a cross at each pair, don't join them, and step back. The crosses climb from the lower left to the upper right, which suggests a positive correlation. Reading correlation off a scatter is mostly about the trend. Points rising from left to right show positive correlation. Points falling show negative. A tight, narrow line means the correlation is strong, whereas a loose, scattered cloud means it's weak, and no pattern at all means little or no correlation. One warning, though. Correlation on its own never proves that one thing causes the other. Let's contrast the two directions. With positive correlation, as x increases y tends to increase too, the points slope upward to the right, and the gradient b comes out positive. Revision hours against test marks is a good example. Negative correlation is the reverse. As x increases, y tends to fall, the points slope downward, and b is negative. Think of a car's age against its resale value. The older it gets, the less it's worth. So what is a line of best fit? It's a single straight line that summarizes the trend in the points, passing as close as it can to all of them. You could draw it by eye, which is quick, but it isn't consistent. Ask 2 people and you'll get 2 slightly different lines. What we need is one agreed rule that fixes the line every time, and that rule is the method of least squares. Here's the idea behind least squares. For each point, the residual is the vertical gap between it and the line. Least squares chooses the line that makes the sum of the squared residuals as small as possible, and we square them so that positive and negative gaps don't simply cancel out. The line we end up with is written y equals a plus bx, where a is the intercept and b is the gradient, and it always passes through the mean point, x bar and y bar. Now, the formulae. Sxy is the sum of xy minus the sum of x times the sum of y, all divided by n. Sxx is the sum of x squared minus the sum of x squared over n. Then the gradient b is simply sxy divided by sxx, and the intercept a is y bar minus b times x bar, where x bar and y bar are just the means of x and y. The order matters. Work out sxy and sxx first, then b, then a. Let's fit a line to our 5 students. With n equal to 5, the sum of x is 15, and the sum of y is 20, so x bar is 3 and y bar is 4. The sum of xy works out to 69, and the sum of x squared to 55. So sxy is 69 minus 60, which is 9, and sxx is 55 minus 45, which is 10. That makes b 9 over 10, so 0.9, and a is 4 minus 0.9 times 3, so 4 minus 2.7, which is 1.3. Our line is y equals 1.3 plus 0.9x. Often, you're just handed the totals. Say a sample of 8 gives a sum of x of 40, sum of y of 120, sum of xy of 680, and sum of x squared of 240. Then x bar is 40 over 8, that's 5, and y bar is 120 over 8, so 15. Sxy is 680 minus 600, so 80, and sxx is 240 minus 200, so 40. That makes b 80 over 40, which is 2, and a is 15 minus 2 times 5, that's 5. The line is y equals 5 plus 2 at... What does the gradient b actually tell you? It's the change in y for every 1 unit rise in x. In our line, y equals 1.3 plus 0.9x. Each extra hour of revision adds 0.9 of a mark. A positive b means y grows as x grows, a negative b means it falls, and the bigger b is in size, the steeper the line. Always state the units. Here it's marks per hour. The intercept a is the value of y when x is 0, in other words, where the line meets the y-axis. In y equals 1.3 plus 0.9x. That a of 1.3 is the predicted mark at 0 hours of revision. But a word of caution, the intercept only really means something if x equals 0 makes sense in context. If 0 sits far outside your data, treat a as setting the height of the line rather than a genuine prediction. Let's read a real example. For a firm, weekly cost in pounds, y and units made, x, follow y equals 500 plus 3x. The intercept of 500 is the fixed cost, £500, even when nothing is made. The gradient of 3 means each extra unit adds £3. So for 120 units, y is 500 plus 3 times 120. 3 times 120 is 360, giving 860. The predicted weekly cost is £860, a fixed £500 plus £3 a unit. Plotting the regression line is easy because it's straight, so you only need 2 points. For the first, put x equal to 0, which gives y equal to a. For the second, pick a large x within your data range and work out its y from the equation. Plot both points, join them with a ruler, and as a check, make sure the line also passes through the mean point, x bar and y bar. Let's draw y equals 1.3 plus 0.9x for the 5 students. At x equals 0, y is 1.3, giving the point 0, 1.3. At x equals 5, y is 1.3 plus 0.9 times 5. That's 1.3 plus 4.5, so 5.8, giving 5, 5.8. Join those two with a ruler. And as a check, at x bar of 3, y is 1.3 plus 2.7, exactly 4, which is y bar. So the line passes neatly through the mean point. The whole payoff of the line is prediction. Substitute a chosen x into y equals a plus bx and work out y to estimate the response. Or, if you're given a y value, you can rearrange to solve for x instead. Just remember, these are estimates, not exact answers. They're only ever as good as the original data, so state your units and round sensibly. Let's predict the mark for a student who revises 3.5 hours, using y equals 1.3 plus 0.9x. Substitute x equals 3.5. 0.9 times 3.5 is 315. Add the 1.3 and you get 4.45. And since 3.5 sits comfortably inside our data range of 1 to 5, this is a reliable interpolation. This brings us to 2 important words. Interpolation means predicting inside the range of your data, and it's usually reliable because real points support the trend. Extrapolation means predicting outside that range, and it's risky because you've no evidence the trend keeps going. The further beyond the data you reach, the less you can trust the answer, so always note which of the two you're doing. Side by side, the contrast is clear. Interpolation is the safer one. Your X lies within the observed data. The trend is backed up by real points. And you can use the estimate with some confidence, predicting Y at 3.5 when the data runs from 1 to 5, say. Extrapolation is the risky one. Your X lies beyond the data. There's no evidence the trend still holds, so predicting Y at 10 from that same 1 to 5 data is something to treat with real caution. Let's test 1. Our data covers X from 1 to 5 with Y equals 1.3 plus 0.9x, and we want Y at X equals 8. Substituting, 0.9 times 8 is 7.2, so Y is 1.3 plus 7.2, that's 8.5. But 8 is well beyond our range of 1 to 5, so this is an extrapolation, and while the number is 8.5, we should treat it with caution. Let's lock in some vocabulary. Least squares is the method that minimizes the total of the squared vertical residuals. A residual is the vertical distance from a data point to the regression line. The gradient, B, is the change in Y for a 1-unit rise in X. And the intercept, A, is the value of Y where the line crosses the Y-axis at X equals 0. And extrapolation, remember, is predicting a Y for an X beyond the data range. A few pointers to keep you on track. Always compute SXY and SXX before B, and keep your decimals accurate along the way. Remember the intercept is Y bar minus B times X bar, not the other way round. Never join scatter points with a line, and do check the regression line passes through the mean point. Never read causation from correlation, and always flag a prediction that extrapolates. Time for a quick check. For n equal to 5, with the sum of x 15, sum of y 20, sum of x y 69, and sum of x squared 55, can you find b and a? In plain words, what does the gradient b tell you? Which 2 points would you use to plot y equals 5 plus 2x? And why must you never join the points on a scatter graph? Have a go before moving on. A second check to finish this part. If your data covers X from 10 to 40, is predicting Y at 55 interpolation or extrapolation? In the cost line Y equals 500 plus 3x, how would you interpret both A and B? Why does least squares square the residuals rather than just add them up? And what's the 1 point every regression line is guaranteed to pass through?